in this section, what we're going to do is we're going to introduce the rules of differentiation that will allow us to take the derivatives in a much easier way. We're not going to have to do the limit process every single time. So just to get us started, let's talk about a little bit about notation. So suppose that you have y equals f of x. You have that equation right there. Then there are different ways you can denote the derivative of the function f of x. For example, you could just call it f prime, you could call it y prime, you could use the differential notation as dy dx, d of f of x dx, or think about it as an operator, d sub x of y. This last one we're not going to use during the class, but just so you know, that can also denote the derivative. So in any case, the differential notation is just a little suggestive of the fact that you're taking a limit as the change in the x coordinate goes to 0 of the change or the ratio between the change of y with respect to x. That's just why we use this notation. And we also have the notation for whenever we're evaluating the derivative at a certain point. For example, if you wanted to evaluate the derivative at x equals to 2, then you would write it as f prime evaluated at 2, or dy by dx, and this bar means evaluated at x equals to 2, and the same for the f of x by dx. So let's take a look at a few of the rules of differentiation. So for example, if you have a constant function, the function y equals 2. Well, what is the derivative in that case? Well, the derivative would be the slope of the tangent line, and when you look at the tangent line to a line is the line itself, right? I mean, if you try to draw a line that is tangent to this at this point, it's just the line itself. And what is the slope of this line? The slope is 0. So we know that d by dx, or the derivative of 2 by dx, is 0. And this is true for any constant function. When you have a constant function, then the derivative of that constant function will be 0. So that's going to be our first rule. The derivative of a constant function is always 0. Then we're going to have the power rule. This is one of our basic differentiation rule. So how does this work? Well, if you have the function f of x equals x to the n, the derivative of it would be n times x to the n minus 1. So for example, if you wanted to calculate the derivative of x cubed, for example, well, you lower the 3, and then you have x to the 3 minus 1. In this case, n is equal to 3, and that is nothing but 3x squared. Okay, you could also do the derivative with respect to x of x to the what? To any number. You can choose pi, for example. Well, that would just be pi x to the pi minus 1. You can choose just about any number there. Okay? Alright, the next rule we have is, well, the next two rules. Let me talk about these together. These two rules together give you the linearity of the derivative. So when you have a constant times a function, you're able to pull the constant out of the derivative. So for example, if you have d by dx of 3x squared, then you're able to pull the 3 out of there and just calculate the derivative of x squared. Now, for the derivative of x squared, well, you just have the power rule that we just did. And what do? Well, copy the 3, and the derivative of x squared is going to be 2, lower the exponent, then x to the 2 minus 1. So subtract 1 from the exponent, and that's going to be 3 times 2 is going to give you 6, and then x to the 2 minus 1 is going to be x to the 1, which is just x itself. And similarly, we could do something like the derivative with respect to x of the function, I don't know, 2x, for example. And what do? Well, you pull the constant out, and then you take the derivative of x, which would be just 2 times, and then the exponent is 1 here. That looks ugly. Let me try again. This exponent is 1. So you lower the 1 and then multiply times x to the 1 minus 1. And then x to the 0 is going to give you 0. And you're going to have just 2. 2 times 1, right? Oh, I said x to 0, 0. X to 0, 1. Sorry about that. Okay. All right. So we have that. Now, the other rule that we have that can be proved just by using the limit definition and the linearity of the limit is basically that you can break up a sum. And how do we use this? Well, in the following way. If you have something like x squared plus x cubed, what do? Well, you can break the sum and calculate the derivative of each term individually. So you could write it as the derivative with respect to x of x squared plus the derivative with respect to x of x cubed. And then that gives you 2, well, I already calculated the derivative, no, never mind. 2 times x to the 2 minus 1, which is going to be 1, and then just 2x plus lower the 3, and then x to the 3 minus 1, which is 2, and that gives you 2x plus 3x squared. So basically you can calculate the derivative of each term individually and then just add them together. Okay, so with these two rules in hand and the power rule, we can calculate derivatives of polynomials. So for example here, if you have f of x equals 3x plus 2, you can do the derivative of this is going to be the derivative of 3x plus the derivative of 2. Okay, derivative of 3x, pull out the 3, derivative of x only, we did it before, it's 1, and derivative of a constant is 0, so plus 0, and I get 3 times 1, which is equal to 3. Okay, so the derivative of this function is just 3. So what does that mean? Well, the slope of this function, the tangent line to this function, is always equal to 3. Well, it makes sense. It is a line. Y equals 3x plus 2 is a line with slope 3, and since the tangent line to a line is the line itself at any point, then you have that the derivative is the slope. Okay, so let's do this one. Y prime is going to be, now let me calculate this derivative quicker. Lower the 4, and then I get x to the 4 minus 1 is 3. Minus derivative of this guy is going to be 7 times x is 7 times the derivative of x. The derivative of x, we said it was 1. So it's going to be 4x cubed minus 7. Okay. What about this one? Well, when you have radicals, it's a lot easier if you write them as powers of rational numbers. So for example here, x to the 1/2. And in that case then you get y prime then is going to be equal to 4 times the derivative of x to the 1/2. To calculate the derivative of x to the 1/2, we do nothing different than we've done before. Lower the exponent, and then you have x to the 1/2 minus 1. And that's going to be, well, the 1/2 times 4 is going to give you a 2, and then you're going to have x to the 1/2 minus 1, negative 1/2. So if you wanted, you could write it as 2 over the square root of x. You could complete the square if you wanted as well. 2 square root of x over x. Did I say complete the square? That's wrong. I meant rationalize the expression. You could do that too. But the way to take the derivative is the same. You pull the constant out and calculate the derivative of this term, which is just going to be 1/2 and then x to the 1/2 minus 1. Okay. So what about something like this? Well, this one you can write again as 4 to the x to the negative 1. That's just when you have x in the denominator is the same as multiplying times x to the negative 1 and then minus x to the 3/5. Sorry. Okay, so your derivative then becomes the following. Well, lower the negative 1. So first copy the 4. Then lower the negative 1 gives you a negative times x to the negative 1 minus 1 is going to be negative 2. Minus, oops, close parenthesis, minus, lower the 3/5 and then x to the 3/5 minus 1. And that gives you negative 4. X to the negative 2, you could put it as x squared in the denominator. And then minus 3/5 and then x to the negative 2/5. And you could also write this as negative 4 over x squared and then minus 3 over 5 and then the 5th root of x squared. That's how you transform this into a radical. Well, that, in my opinion, this is just a matter of style. You can leave it in either way. I think that's perfectly fine. Alright, let's do a couple more. So for example, this one. What do you do when you have decimals? Well, that's going to happen a lot whenever we're talking about money or quantities in business. So when we have the expressions of this form, does it change anything? Well, it doesn't. They're just a constant, so you pull it out of your derivative, so 0.01 times the derivative of x squared. For the derivative of x squared, you get 2 times x to the 2 minus 1, so just 2x, and then plus 0.4 times the derivative of x, which we said was 1, plus the derivative of 50, that's a constant, so that's 0. So you just get negative 0.02x plus 0.4. So there's nothing different. It's just what numbers you use. Okay, I lied to you. I have 2 more now. So if you want to take this derivative, what do? Well, again, you write it in terms of a fractional exponent, and this one you write it as a -1, and now you're able to use your power rule. So with that, then you just write it as 1/5 of that doesn't look like a 5. 1/5 of x to the 1/5 minus 1, -4/5, and then minus 2 times, and then lower the -1, and then times x to the -1 minus 1 is going to be -2. So that's going to give you something like, I'm going to leave it in terms of fractional exponents this time, just not to bore you with more. I said fractional, and let me leave it with negative exponents too. So I'll leave it at that. So just not to bore you with more simplifications. Okay, one last one. If you have the expression y equals x plus 2 over x cubed, and you want to find the derivative evaluated at a point or at a value of x, what do? Well, you just take your derivative first. So you write dy by dx, and then the derivative of x is going to be 1. And I should have written this one firstly. Let me rewrite y for you. It's just going to be x plus 2 times x to the -3. Now you can apply your power rule. You'll get used to doing it without having to write it in that form, but since this is our first time doing it, I want to write it all clearly. So here now, 2 times the derivative of x to the -3, so it's just going to be lower than -3. X to the -3 minus 1 is -4. So then your derivative is 1 minus 6. I'm just multiplying 2 times 3. X to the -4th, and if I'm on -4, and I'm going to evaluate it at x equals 1. So when I evaluate this at x equals 1, that looks ugly, not any better, but it's x equals 1. You plug it in here, you get 1 minus 6 times 1 to the -4, it's just 1 again. So 1 minus 6, -5. And that's all you do. Alright, so now you should be ready to calculate all these different derivatives. Alright, I'm going to stop right here and I'm going to continue with some more examples in the next video. Thank you so much for watching, and until next time.